Good evening, everyone. I'm audible. We'll start with today's training session. So our topic for the day is basic pipe stress analysis methods, part 1. Today we'll be covering the part 1 and tomorrow we'll be covering the part 2. Let's meet our trainer for the day. Our trainer for the day is Mr. Stephen Raphael Babu. He's working as an associate engineer in iFruits Engineering. He has over 6+ years of expertise in mechanical piping engineering drafting, stress analysis modeling, pipe supports, and AutoCAD. He has been an integral part of several quality projects of iFlux Engineering in the past years. I happily welcome Stephen to the training. And also, I request everyone to please mute your mics.
Hello, everyone. Can we start that training? Today, our section, 1 minute, I will share my screen. Hope everyone, my screen is visible. So today we are going to see the piping stress analysis, basic stress analysis. What are the things we record for piping stress analysis? We need to go through that before going to the CISA software. So what I am going to plan is first section today, we are going to tell about the basic things, and tomorrow we are going that software introductions. Okay, let's start.
Stephen,
Yes.
your slide is not visible. I think you have opened the other screen.
1 minute, ma'am.
Yeah.
Now it's visible, ma'am?
Yeah, now it's visible. Yes.
Yes. So let's start. What we are going to learn today is displacement, stress, and strain field, modulus of elasticity, stress and tensor, longitudinal stress, radial stress, circumferential stress, and moment of inertia, stress strain curve. So these are the basic things we learn from the engineering sites. So before going to enter into this, the CISA software piping stress analysis, we need to know these things, because that calculation, if you are going to do it in manual way, you have to know these are also. So first we learn these things and we will go to that next part. Okay, that what is stress? Let me say, think if your stress is nothing but something not usual, cannot be sustained for a long and unexpected. For example, if you are in home, so you are stress free. If we went out of the room, your home, you have to face a lot of troubles and a lot of things you have to face. So lot of problems you have to face. So the stress, that is stress. Okay, so stress.
Sorry, Stephen. Can you make the
Yes,
slide in slideshow?
yes.
Yeah, thank you.
Yes, that this stress. So for example, if you see, this is the process plant. You have a lot of pipings, pipelines, columns. That means columns, the heat exchangers, these things and also would be there. But if you see, uh, for example, if you are in the top of the building, you are standing in the top of the building. For example, can I use that painting? Okay. You are in the top of the building. Okay, 1 minute, I will delete this. It is a 9th floor, it's up to 9th floor. You are standing here. For example, if the wind is coming from here, this direction, what happened? It will, you got fear because you are in the edge, you may fall down. It's coming because of fear, right? Likewise, if you have some wings in your body, then what happened? You definitely fall down, but that surface area of the wing is like it's act like, hello. So wind act like, so like this. If the wind is acting here, so you definitely fall down from the edge of the building. So it may happen because, for example, likewise, what I am telling here is that the wind is depend upon the surface area. So if the piping is here, if the piping is coming from here, it is connected from here, what happen if the wind is acting here? So that whole body is affected by the wind. And likewise, if the if you go near to the heat exchanger, that what happen means that that heat exchanger outcome pipe will be more heat, so it will be more heated. So what the stress analysis stress engineer uh, need to do means we need to anticipate what we need to do to save the pipe. Likewise, so if we fail to anticipate that, that pipe will be damaged and it will come to uh, more explosive and it will be more hazardous to everyone. So next one is why we are going to do the stress analysis. So the piping contains fittings, network piping contains piping, walls, fittings, and process equipments to carry the fluids. Like so that there is some loads will be act while uh, by using the temperature, pressure, earthquake, wind, PSV, thrust, vibration loads, etc. By using this occasional and sustained loads, that pipe will be damaged and it will be it going to broken, and it will that more of the at the end that the cost and the people who are there, it will be very dangerous in dangerous situations. So first, for example, if the earthquake comes, what happen? That weight of the, for example, if you are having a tank with the supports, it supports in the earth. So if the suddenly the earthquake will happen, what happen means that soil properties will be eroded and it will come down. So that the tank depend upon the tank weight, it will go down. So it is unexpected. So in the first slide itself, I tell you that something are not usual cannot sustain for a long time and unexpected is stress. So that the definition of stress is the piping system experience load, force, and sustainably that stress due to various factors like temperature, pressure, earthquake, wind, PSVs, vibrations, etc. So what are the loads are going to act on this piping? We are knowing, we need to know that first is sustained loads. Sustained load is nothing but that weight of the pipe. So every pipe depend upon that size, the weight of the pipe is differ. Pipe, uh, wall weight, fittings weights, and some other process equipments are connected in connected instrumentation instrument. we don't need to include it in the stress analysis, but it will happen. That weight and all will come in the pipe while supporting, and it will make us, if the support is not given in the proper way, the pipes will become damaged. So next one is thermal load. Due to high thermal temperature, that expansion will happen. So expansion, compression, expansion, compression. So fatigue failure will happen. Uh, that fatigue failure will happen once in 20 years or something like that. It will not suddenly happen, but if the temperature is high, what happen? It will be expand. But nearby the equipment, what will happen? For example, if I am showing this thing, this should be the tank, and tank, and another tank is here. We are going to connect that pipe from here to here. If I am not supporting the pipe in proper way, in not in the proper way, what happen? If that due to the thermal expansion, it will go like this, because this is due to high temperature. I am telling is it's for an example. For example, this one is a heat exchanger, like that you mentioned that, because the tank doesn't have that much temperature. So we are going to do it in that heat exchanger. So what happened? It will expand like this, and it will, so that this will not in this area is not in safe condition, because if it is more than that, more than its allowable stress, it will broke the elbows and the pipe will be broken. So we need to support it in a proper way, and we have to maintain the thermal expansions. And next one is occasional. Occasional, it will come occasional only due to heavy rain, due to sustained, seismic, uh, snow loads, PSV, pressure safety valve release, these things and all, it will come under the occasional load. And dynamic load is a vibration analysis. Due to vibration, what will happen? Water hammers, these things under, it will come under dynamic load. So next thing, before going to this, we all knows that material is made up of molecules and atoms. If the material is splitted into small pieces, it will give you atomic structures, like BCC, FCC, like that. You know that BCC is body center cubic and FCC is face center cubic. These two are mainly we are used in the mechanical piping stress analysis, because if we, for example, if you are going to put the steel in a, for example, if you are steel pipe is there, so if you are expand or anything, it will happen if the stress is acting on the pipe. So this PCC will be converted into FCC. So FCC molecule is like this. So this will be more dense than the BCC. So this molecule will define the force, where the force will be acting. So stress is a restraint developed in the material per unit area under the action of force. So stress is, we already know that stress is equal to load by area. So that's only we have done. So everyone knows that about the BCC and FCC, phase center cubic and body center cubic. So that it will change from face center to body center body center cubic to face center cubic depend on the stress act on the pipes. So brittle and ductility, we already know that carbon contained in the ferrous, it will give you the brittlety and ductility. If it is less than 2%, it is more ductile. If it is less than less carbon, uh, sorry, if the carbon level is less than 2%, it is more ductile, and if it is more than 2% is brittle. So what is brittle? Brittle is nothing but it will broke into small pieces like glasses. Okay, ductile is more stiffness and more this thing will be happen. So expansion coefficient of CS carbon steel is 0.1011 per meter per degree Celsius, and expansion coefficient of stainless steel is 0.017 per meter per degree Celsius. So less carbon is more ductile and more carbon is more hardness. For example, this is the drawing we have to know. So steel having more ductile, and cemental is having more hardness and brittle in nature. So it will not take more uh, force to break it into pieces. So before we are going to stress strain curve, we need to know about that scalar, vector, and tensor. We already know that scalar is a unit vector which has no magnitude. For example, if we have a length, we only mentioned the length, 2 meter length and 3 meter length. We didn't know that the directions. So the vector having the magnitude and the directions. That tensor is we need to give more forces, more thing like um, directions, everything it will become under the tensor. So for example, which one that main important thing in stress analysis is stress, strain, and displacement. So in these three, which one is coming first? We need to know. So which whether it is a stress will come first, or strain will come first, or displacement will come first. For example, if you are going to see this stress strain curve, this is been learned in the engineering page. So up to the yield strength, it will come to the original position. Due to next, it will go to some expansion, and after that, it will be going to the bottleneck necking formation, and then it will come to fracture. This is the simple example. We done it in the we are used in the engineering stage. Um, this is the material. We are giving the force in downward direction. What will happen? It will elongate into some stage. This one is del L. original length is L. We already know that strain is equal to change in length by original length. So strain equal to change length divided by original length. So it will be L. So for example, if we are applying another one force over here, what will happen? So strain is equal to change in length. So change in delta L, del L divided by original length plus elongated length. Change in that del L1. We check it as L1. Okay. L1 plus original length. If you are doing like this, what will happen? It will give you that more calculation and more thing. It will be very difficult to analyze, find out the strain. What they are done is that length will be remain constant if you apply any force. How many force, whether you apply, how many force you are applying, it's not, doesn't matter. The only thing is that length will be equal. So strain equal to change in length del 1 plus del 2 divided by original length. It will be appear like this. If your that length will be in the constant only. So why I am doing this, you will know that once I will come to this stress strain curve. Okay. Next one is stress. In stress, for example, if you are going to give that this thing, going to give the force over here, so there will be change in area. Area will be elongated first like this. If you keep on giving this thing, what will happen? It will change into bottleneck condition like this, right? But if you see in the stress strain curve, it will be like this. 1 minute. Yes. This is the original stress strain curve. But if you change the area, what will happen? That stress also will be increased. Then this one is wrong. No, this one is correct. But the area will be in the constant. They are saying like area is in constant. Okay. Now let's see here. So force equal to E into delta L, because that in depending upon the Hooke's law, the stress is equal to strain. So stress equal to instead of directly proportional, we have to insert the elastic modulus into strain. So F is equal to stress is equal to, we already know that force by unit area equal to E and change in length by original length. Here, what I said, that L and A is in constant, right? So F is equal to E. I need to find out the force. So E A by L at delta L. I am shifting everything except this force. Okay. This force, sorry, we have to correlate with the stiffness. We know that we have the spring like this. We are going to put on 10 kgs this thing. It will be 10 kg like that. So what happened? This spring we have it as K is the stiffness. If I put the force, what will happen? It will change into the length. So it will be delta. So that force is equal to A into delta. We have to correlate these two formulas in one. So F, it will be same K into delta. Delta and delta L is same. So the stiffness is equal to K is equal to EA divided by L into delta L. EA into L divided by L. Okay. So for example, if you are having a pipe, is attached in the one side of the area, force is acting in this direction. What is the stiffness? So K, this stiffness is equal to this. K is equal to EA. This one is area and this one is length. Length. This one is area. So that stiffness value is equal to Ke divided by L. Please memorize this formulas. This is very important in that stress analysis, everything, everywhere. So next one is this. Yes. So why I am asking that displacement, these things and all constant, what I explained in previous slide. Now we are going to enter that things. Okay. That first thing, if you are going this much area, only we are going to consider. Okay. For example, if you are going in the stress strain curve, I'm just, this one is stress. X-axis is stress, strain.
Stasyon yapma. Pas hemen üstte.
Yes. I am only going to consider this alone. So if I am going to give some force for getting the stress, I am going to giving the force up to this level. What will happen? It will displace up to this, right? While giving the force, that the stress will appear like this only. So this one, it will displace. If you are up, how much force is applying, that much displacement it will take first. So here strain is, we already know, delta L, change in length divided by original length. Delta L divided by original length. Stress is nothing but force by area. So if we find out the displacement, we can find out the strain for next, and afterwards only we are going to find out the stress. So it will be correlated, because first we are going to find out the displacement field, and next we are going to find out by using that displacement field, we are going to find out the strain, and by using the strain only we are going to go for the stress. So stress will not come first, that displacement field is coming first. The displacement field, strain field, and stress field. And if you are seeing that the stress is scalar, what will be this? It will be the scalar or vector or tensor. Definitely the stress is a tensor. Next slide is state of stress. For example, if you are going to see this pipe, is there. This is longitudinal stress. Which one is axial and which one is circumferential? We need to find out that things. See, you are saying like y is circumferential, radial, or z is circumferential. Like that we are checking, means it is not like that. What we are going to do, we are going for a stress analysis, we are not going for the full material, we are going for a single piece. We are going to cut it into small pieces, and we are going to see the three-dimensional structure into the two-dimensional structure like this. If you are going to see from the top, this one is longitudinal and this one is circumferential. So for example, this one is x is longitudinal and this is circumferential. What about radial? We are not going to consider the radial, because that radial, that outer atmospheric pressure is equal to the inner pressure inside the pressure of the pipe. So it will be equal to 0. So we are not going to consider the radial stress while using the stress analysis. This one is happen in the Caesar. Okay, if we are going that thing, that three-dimensional material into, we are going to convert it into two-dimensional, and that value is going to go in the Caesar file. That stress, we have it in tensor. Stress is tensor, right? We are going to give some forces, or we are going to cut it into small pieces and give that small pieces will be like this cube. Okay, this cube will be like this. Force acting on the surface in everywhere. This is the force, sigma yy, sigma xx, and sigma zz. This is the force acting on that. This force we already know that force is acting that perpendicular direction, that shear force will be act. So that state, to find out the state of stress, we minimum need 9 different shear stresses required. Okay. Next one is type of stresses. One is tensor, compression, torsion, shear, and bending. Tension is nothing but if you are going to pull on two side, it will be tension stress. Compression, if you are going to compress towards opposite direction, it will be sorry, not opposite direction, in the same direction, it will be the compression. And torsion is rotating. Shear is nothing but if you are going to like two hands, we are uh, like shear it, it will be a shear stress. Like what we shown in the figure, we are giving the opposite direction and inward and outward direction, it will be the shear, that surface is going to shear that. And bending stress, it's a combined stress, it's a big stress, because if you are bending that one, that outer surface we are having is tension, and inner surface is a compression stress. Both are coming under that same stress itself. So shear, shear stress. Um, what I am saying is shear stress. It's a material that force is acting in a downward direction. So which stress is going to act here? It's may everyone says it would be the tensor, because it's going down, it will be elongate, and it will be a tensor stress. But we have a plane, a lot of planes are available in here, so that if the plane is acted, then in the material, then it will be the force. This one will be the force, and here we need to act, that shear force will be acted. The shear force is a byproduct of the stress. If the plane doesn't have a shear stress, then it will be the principal plane. That plane will be considered as a principal plane. Okay. So shear stress, there some plane is there, so the stress is acting, so that shear is perpendicular to the what stress is acting, so that shear will become here. This is the example what we mentioned, what I explained in the painting. Next one is Poisson ratio. Poisson ratio, we are saying like lateral strain by linear strain. So lateral strain is nothing but the diameter, change in diameter by original diameter divided by change in length by original length. This is the Poisson ratio. The general value of CS and SS is 0.3. It is that Poisson ratio only used in the pipeline session only, because it has only a long pipe. It will be considered in the pipeline stress analysis, but we are going to do in a piping stress analysis. We didn't consider that one. So assumption, what we are going to take that assumption is nothing. If the force is acting, what happen means that stress value will not be same. It will be somewhere it will be higher, somewhere it will be lesser. But we are assuming that average stress. We are assuming that average stress is considered in the stress analysis. So Newton first law, we already know that when the object is in the without any forces, that object in the rest condition, that Newton law first, it says that Newton first law, the object is in rest, remain at rest, there is no motions, motion is remaining constant, velocity unless acted on the net. If any external force is acted till the body is rest, it's known as Newton's law. Likewise, if for example, if you are going to see the pressure pipe, if some external force some external force like vibration, these things will happen, this Newton's law will be applicable. So example is pressurized pipe. So important properties of material is nothing, strength, stiffness, and elasticity. Strength depend upon the material, that strength will be varied. It will be that Ashwin will explain everything about the ASME B31.3, the allowable stress, these things and all. Strength, that strength, it will be failed, right? That failure it will come. So mode of failure, it will be considered into 4 parts. One is brittle. We already seen in that the carbon level is more high, it will be brittle and hardness. And ductile, that stress strain curve we seen that normal thing is ductile one. Fatigue failure we already discussed, because due to some elongation, thermal expansion, elongation and compression, that will happen more than 10 years like that. So it will not suddenly happen, it will come later. Creep is nothing but when the pipe is supported in pipe is supported, if the pipe temperature is too high, it will be along deform, and it will be come like this. Then it will, it says like the creep. For example, if you are having a pipe with supports, this one is pipe and this is supports, due to high temperature, what's happened, this pipe yes this pipe will elongate, deform like this. This failure, this type of failure is we called as um, creep. And next one is stiffness. If the deformation occur easily, it will be more flexible. If the deformation occur more this thing more hard, it will be stiffness, the stiffness of material is high. Elasticity, it's same, it will retain its original position, it's known as elasticity. Basic stress concept, longitudinal stress, hook stress, radial stress, and bending stress, shear stress. We are going to see how that formula will appear. So I will go to the paint. It will be very easy to tell you. For example, if you have a pipe, like this. So internally we have some pressure. This one is internal one. Okay. It's having pressure. This is area inside one. So AI, I'm mentioning like AI. This one having a diameter D. This thickness, this one is thickness. Outer area I mention as AO. Okay. AO. So we know that stress is equal to force by area. Area. So here that force is internal force. What is happened? Pressure into PI. Pressure into AI. Force equal to pressure into AI. And the outer that area is equal to I by 4. Outside diameter minus inside diameter is should be the area. So DO square minus DI square. So if we apply this stress, S is equal to P into AI divided by this one, this area pi by 4 PO square minus DI square. Force is equal to pi by 4 AI and area is equal to pi by 4 D outside square minus DI inside square. So we are going to apply it in the stress. So force equal to PAI, sorry, PAI. PAI divided by pi by 4 d0 square minus di square, outside diameter and inside diameter. So if area inside is also a circular, so pi by 4 di square divided by pi by 4. This one is a square minus b square formula is coming. So d0 plus di into d0 minus di. So that pi by 4 and pi by 4 is cancelled. P di square divided by d0 plus di d0 minus di is appear here. So this one, what I am going to do is I am going to multiply into 4 and divided by 4. Okay. So P di square divided by d0 plus di divided by 2 into d0 minus di divided by 2. I am changing this 4 into like this, and 1 by 4 is remaining same. This 4 I'm going to get down and divided by 2. I split it into two things. So d0 plus di by 2 is nothing but mean diameter, and d0 minus di divided by 2 is that thickness, right? And if we apply it here, P di square divided by dm 4dm into t, that di square by dm is nothing but outer diameter of the pipe. So P do divided by 4t is the longitudinal stress. Hope you understand this thing. This equation is we need to learn because it will be helpful, because it will be used in the stress analysis. While doing the stress, you will learn how it will be, why we are learned these things and all. Okay. Next one is hook stress. Hoop stress. For example, if the pipe is there, okay, during the hydro test, that pipe is cracked. What is hydro test? Hydro test, why we are using hydro test is nothing. We are going to see the pipe will be withstand with that temperature or pressure. Nothing but the leakage test. We have to see the leakage. that at the same temperature and pressure, that leakage will be happen or not. It is known as hydro test. It will be conducted before that pipe is going to attach in with the equipment or anywhere. We have to do the hydro test. While doing the hydro test, what happen if, for example, I am saying that that leakage is coming, leakage is coming. So what will happen? The force will be appeared here, and that leakage force will be appear here, right? In this way, we have to see. It will be like this. So force will be appear here. That liquid will come down with high pressure. So in hydro test, that pressure will be 1.25 times higher than the original pressure. So let's see. I am going to take that single piece from here. Okay, this piece. I'm going to not going to do for all the things, so only for this. So if this is the rectangle, this is the area it's acting, and this will be the length, and this will be the diameter. The force is acting over here, and this will be the thickness. So stress is equal to P into area divided by resistance load. So what happened? 1 minute. DOL divided by so diameter outside that area will be length into diameter, PDO divided by L, that outside diameter, and the force acting inside that area is 2 times of T into L, because that T is also appear here. So 2 T's divided by into L. Okay, so L will be cancelled. So PDO divided by 2T. We mentioned that that's SL, longitudinal stress is PDO divided by 4T. So Hooke stress is PDO outside diameter divided by 4T. So Hooke stress is twice greater than longitudinal stress, right? It will be twice. If the longitudinal will be 100 means that Hooke stress will be 200. It will be the twice of this longitudinal stress. That formula you maintain, memorize this thing, and afterwards that radial stress. Radial stress, what I mentioned before, we are going to change that three-dimensional problem into two-dimensional. So we are going to neglect that radial stress. Why? Because that pressure acting the atmosphere and inside the pressure is equal to 0. So radial stress will be equal to 0. Okay. Then we are going to bending stress. Bending stress, we know that we learn it from 1 minute. So these things for thin cylinder and thick cylinder, what we are mentioned, the so sigma A is nothing but the axial or longitudinal stress. We mentioned in the diameter, but here I mentioned in R. So PR divided by 2T for thin cylinder. Okay, thin cylinder is nothing but the Di by T is less than equal to 20. If it is less than 20, it will be a thin cylinder. If it is more than 20, it will be a thick cylinder. We are not considering this thing because we are not going to do this in the stress. For example, if you are that's a thick cylinder and all, it will come later. It will be that big subject. So I am just mentioning here. So sigma T is a Hooke stress, PR divided by T. We done it BD divided by 2T. Here BD divided by 4T. Radial stress will be negligible, so it will be equal to 0. And then we are going to bending stress. Bending stress, we already know that in the engineering side, we know that formula. I'll do that. M by I is equal to sigma Y. That means stress, bending stress by Y equal to E by R. So what is M? M is bending moment. Uh, for example, if you are going to use this and it will be the L, length will be L, and the force is acting downwards, what will happen? It will go like this, right? So bending stress is equal to, bending moment M is equal to F into L, right? For example, if you are having a pipe with 3 supports having some walls over here, so that force is acting here. So what should be the bending moment? You said like F M is equal to F into L. How? Because if we applying some that means if you are applying the force, what will happen? This line is going long. It's not a problem, but it is only in the rest condition only. It's not in the hold or it is in the weld condition. So it will tilt. It will be like this. There is no moments. It will rotate like twist. Okay. So bending moment is nothing but if you are how much time it will be longer it will take. M is equal to force into length, and I is moment of inertia. We already know the for a rectangular moment of inertia for rectangle it will be the height b. It is h. So moment of inertia is equal to bh cube divided by 12. We learn it from the engineering. So for circular, pi by 64 into d04 outside diameter and inside diameter. This is the formula for momentum of inertia. Yes, moment of inertia. Bending stress. Um, bending stress. Yes, sigma. First, initially, we need to go to y. Y, what is y? Y is distance to the fiber. So, for example, if the center is elongated in this way, so that outside diameter is fixed, right? So, how much distance it will move? That is y. Y is equal to r, ro, outside radius. This radius will not change because that I said like this one diameter is same. So r0. So we will go to stress. Bending stress. First, we will take these two. Mi is equal to stress by y. So I need only the stress. So m y divided by I. We already know that m, I am going to get this thing here. So I by y is nothing but section modulus z. So that bending stress is equal to m by z. Okay, er it will be taken, but this two are the most important thing you have to learn. So m by z. M is bending moment and z is section modulus. Okay. Next one is torsional stress. Both this what bending stress and the torsional stress are equal. 1 minute, I am showing that. We are going to compare the both equation. M by I equal to stress B, bending stress divided by small y, that is that center, equal to E by R. This is one. This one is for bending. Next one is torsional. Stress is equal to M T divided by J equal to tau by R equal to C delta E by L. So if you are comparing this, both are same. So MT is torque, tau is polar momentum inertia, and T tau is shear. Sorry, J is polar moment of inertia. Tau is shear stress. R is radius of pipe. C delta, C is modulus of rigidity, delta is an angle of twist, L is the radiance. What I mentioned here is same as what is mentioned here. So we are going to do the J. So J is equal to, we already know, Ixx plus Iyy. So J is equal to 2I. Okay. So we are going to apply here. So tau, sorry, M by I. So MT by J is equal to tau by R. So what I needed is tau. So M T R divided by J. So what I mentioned here, J is equal to M T R divided by 2I. So M T divided by 2I by R. So we already mentioned that I by R is equal to Z. So MT divided by 2Z. This is shear stress formula. MT divided by 2Z. Okay. So these are the basic things we have to learn. We will give you one calculations regarding this. If you done that, we will learn next session. We learn about the Moore circle. In that Moore circle, you know how that stress software is working and how we will create the model and everything and all. Today is that's all, ma'am.
Yes, sir. Okay, we conclude today's session. We'll move to the Q&A. I will share the link to you so you can address the questions. Sir, I've sent the link in chat to you. You can just open that link and you'll find the questions. You can, if you want, you can stop sharing the screen. Hope you're able to view the questions. I will share the attendance link shortly. Are you able to view the questions, Stephen? Hello? Stephen, are you there? You're on mute, I think.
Oh, sorry, ma'am. I'm in mute. I will
Yeah,
explain.
yeah. You're able to view
Yes.
the questions, right?
Yes, ma'am. Yes, ma'am.
Okay, okay. You can answer all the relevant ones.
Yes, ma'am. Uh, so, what are the input record and expected output of stress analysis? For example, for stress analysis, we record input is uh, that GA, PNID. Um, PNID, we can know that material selection and these things and all we record. That the main thing is PMI. Uh, and GA drawings, PNIDs, temperature, pressure, and these things are the main input we have to inserted in the stress analysis. And expected acceptance criteria is depend on the client. Uh, Normally that expansion, there is four things happen: hydro, sustain, occasional, and thermal. Thermal, we gave from 80 to 90 per 60 to 90 percentage, but it's depend on the client, what they are given in the stress design basis. We have to know, we have to learn from from the design basis. How to estimate the vibration load? Vibration load, it's a different things because it's a dynamic analysis. Uh, we can, but now it's in the initial stage, we can't able to explain that one. It's a different path. What we are doing is only the static. The dynamic we record, we can do it, and we will tell you later, no problem. Kindly explain a stress strain curve again, it will confuse to think the explain in the paint. Okay, so strain curve, why I am explaining this stress strain curve is, see, this is considered, this is a material. Okay, if the material we are giving the pressure, temperature or something like that, it will be elongated up to this yield strength. After that it will move up to here, it will not elongated, it will stop here itself, that original position. For example, if you are if you are pulling the rubber from one both the end, what happen, it will up to that yield strength, it will happen. And next thing, it will not happen, it will broken, or it will come like that, it will not come to the original position, it is the ultimate strength. If we are giving, still we are giving the force or temperature like that, it will broke sometime. At some time it will give you the bottleneck formation, and it will give you the fracture. Okay, here they explain only, they explain it by using area and the length in the constant. Okay, if for example, if you are doing in a real way, what happen is this stress strain curve is not like this, it will be go like this. So here they are saying that this, for stress, the area is constant and that length constant. In, if you need to find out the stress, what we need to find first, initially we need to find the displacement, and then by using that displacement, that length you find out, that change in length we can find. So if we apply some force here, what happen, it, that same displacement, that same same thing, it happen in y direction. If we apply any force over here, the small amount of force is applying in the stress, then the strain will also be changed, because stress is directly proportional to strain. So the stress is that strain is also changed. So in here we can find out the length by using that. So by using the length, we can find out the strain, and after that only we can find out the stress. This is the thing. This way we have to find out the stress. Okay. Next thing is what does tensor mean? Tensor means it's just like a matrix. If you are seeing that 3x3 matrix, 4x4 matrix, you learn it in the engineering. So if we need to give in the finite element analysis, you learn this 3x3, 4x4 matrix and all. So in tensor, if we applying the force in the plane, that means if you are applying the force in the plane, that xy direction, it will that z direction is showing the plane, that force is acting on the z direction. So that is a lot of input we record to know the state of stress. So tensor is depend on tensor is stress is as tensor mode. So that scalar and vector and all, we have a length only, and dimension direction if you give means it will be vector. But here we have to show if the force is acting on the plane, that shear force will be active perpendicular to the directions. So that extra force, extra shear stress is acting. So minimum 3 stress value will be appear in the same what same plane. So it is tensor. Okay, there is uh, more than scalar and a vector. It is tensor. Kindly explain shear stress again. Sure. Shear. Um, shear. While you are in a cold condition, what you will do? You will we will you will what you will do like this, right? That both the hand will be shear like that. That means you will produce the heat. It will be very easy. So shear is nothing but that plane. It will be sliding over up and down. It is known as shear stress again. And how the supports and support distance will be calculated. We have if you see some based that these things, if you are using a pipe data pro or something like that, they will already calculated that things. Otherwise you have to go for the standard what they given in the stress design basis and all. They will give you each support will be in 6 meters, these things. uh, Otherwise, if you are constructing a new one, we have to introduce the support. It will be rest support, it will be guide support. That support will be different. That will be explained in next section. We can explain. Which can run without any support. Please explain the relative between spring support and stress analysis. Oh, how the stress value affecting the necessary of support. The stress is not affecting the support. That stress value affecting the necessary supports. For example, if you are running a pipe with a 6 meter length, 6 meter distance, we are giving the supports. No problems. If that stress value is depend upon what I explained in previous slide, in the first slide, the stress will be acted depending upon the pressure, temperature, and that will be happen any of this things. But if, for example, if you are having expansion, what happen if you are not supporting the well, supporting it in a proper way, it will happen, no, it will expanded up to the limited. If it is in the yield strength, it will be okay. If it is expanded more than the allowable stress, then the support will need to be exchanged by using the bellows like that. uh, Di square and dm squared is equal to outside diameter. How? Di square and dm square, if you di square and dm square is equal to outside diameter, what I explained in the shear stress, right? Sorry, in the bending stress. Yes, di inside square. uh, I will explain it next section. No problem. Please explain how the stress analysis will be done in a real time. Could you please explain the process? How all the involved? What are the all input record? So initially we need to that process will be like this. We need to set that units. What are the units they client record? Depend upon that thing, we can find out that these things, that unit will be changed depending upon that mmr we needed in the meter. Because if the drawing is in meter, we need to change it into, if we have to convert it into if we are putting the input in we need to change into meter. So it will be the higher process. So first initially we will do uh, first we will do that these things, units set. I need to set the units, and we need to fix the north, which one will be the north direction, whether if we need to put the y as a north or x as a z, z as a north. We need to fix that one, and after that we need to go inside and put the new models. uh, it's the input record is isometric. uh, if we are connected with some other equipments, we need the equipment GA drawings, because while expansion, that while processing, that there should be the expansion. Even 1 of expansion will affect the pipe. It will affect the nozzle load. So we need to draw the whole thing, GA drawings. Sorry, we need to draw that. We need to model that equipment also inside. We need to input material. We need to select the material. We need to select the codes, and after that we need to model that one, and we need to give that load cases, wind loads, seismic loads values, everything we need to put it. We will do it in the next session. We will tell you clearly. Now that allowable stress, how to calculate. So allowable stress, it will be already calculated, because that material, that that ASME guys, they already calculated and kept it in the tabular column in the ASME B31.3. You can see that in the that process. That calculation will tell you how it will happen, because today I'm going to give you two sums. Instead of that sum, you can find out that how that allowable stress is calculated. And these things we will continue in tomorrow session, because that more circle is more important while you are seeing that things. What we need 3D modeling is or isometric is sufficient. Isometric is sufficient because we need to know about the length, how much length it will going to north direction, east direction. That is enough for 3D modeling. No need of going to GA drawings. We need a piping material specification PMS because that thickness, these things we need to check it from that. 1 mm will affect the pipeline during the construction and the real time it is what's possible to save 1 mm. See that pipeline, I am not saying that piping will affect that nozzle load. That is should be the nozzle load is there. So if the equipment is having equipment is connected with the piping due to some, for example, if you are in a column, the temperature will be increases and decreases. It will be connected with the piping only, that nozzle. If the inside fluid will be high temperature, that depend upon the temperature that equipment will be elongated. So on that time, that elongation will be high. So what we do, that 1 mm elongation also will be affected. So we need to do that uh, before that before not in the real time. We will need to give the supports depend upon that 1 mm. How if the expansion is changing, we need to know where to support and where to here. That support will help you to from the higher explosion or everything. So be sure always there will be more dimensional changes more than 1 mm. No, it will not affect, but even 1 mm displacement will happen if we need to do that things because uh, we need to model that. Why I am saying is we need to model that equipment. Even for example, if 1 centimeter, it's 1 meter, 1 mm is increasing means, what about that other things? That temperature is inside, no? So that is depend upon that things. So 1 meter, it will be 1 mm is increasing. So 2 meter, how much amount it will be increased? So it will affect that. That's why I'm saying. And so what are the feed required to select the spring supports and the other supports as well? Feeds you record what type of spring is there. We need to know that. By using that selection itself, they will calculated and give you that things. But some of the input we need to insert it. I will explain it in some other days. Minimum length, how much? Yes, ma'am. Hello, ma'am.
Yes, sir. Yes, sir.
Yes, ma'am.
So
Yes, ma'am.
we have done with the Q&A, right?
Yes, ma'am.
Okay, sir. Then we'll conclude the session. I hope there's no more doubt for anyone. If you have any doubt, you can just unmute yourself and ask. If there's no doubt, we can conclude today's session and continue tomorrow. I think there's no more doubts. Thank you, sir. Thank you for taking the session in a very short notice. Thank you so much. And also, thank you all participants for actively participating in this training program. You'll have today's assessment assessment exam for today's module on tomorrow, 11 to 11:30 a.m. IST. So thank you, everyone. Thank you, sir. We'll
Thank you,
see
ma'am.
tomorrow. Thank you.